að Björn Jónsson ætlar að taka smá umræðu við okkur Big Data og ástæða fyrir ég stofnaði nú fyrirtæki mitt á sínum tíma var að ég las mikið erlendur rannsóknum og það sýna 10–50% af tíma fólks fyrir að leita gögnum eða skrá óþarfa gögn og gagnamagn alltaf verða meira og meira og það skiptir miklu mála að svona finna réttu gögnin og þegar taka ákvarðan að taka ákvarðan út frá réttum gögnum og líka aðgengi sé rétt. En Björn Jónsson hefur starfað tölvunarfræðideild HR í 1,5 áratug tíma sem deildarforseti. Hann hefur einhvers stundar rannsóknir á afköstum margmiðlunar gagnagrunna og hafa þær rannsóknir meðal annars leitt í stofnunar sprotafyrirtækisins Identified Technologies. Hann rannsakar núna samruna gagnagnóttar, Big Data og margmiðlunar gagna. Og Big Data eitthvað sem mun verða alltaf meira og meira áberandi næsta árin. Velkomin, gjörðu svo vel.
Okay, thank you. So I promised to give this in English, and so for those of you that missed the introduction, I'm Björn. I do some analytic stuff at Reykjavík University. So I'm going to talk about big data management. Now we had Ingrid talking before about analytics, which is represent a lot of the use cases for big data. But I'm basically going to go a little bit more, not very deep, but a little bit more to the basics of this, the underground world, and a little bit nerdy, more nerdy, I would say, than some of the things you've seen where people talk about big data and they wave their hands a lot and they tell you that on the scale of 1 to 10 of usability, where the wheel is 9 and your opposable thumb is 10, then big data is 11. So I might not do that. So you can also say if somebody comes in and tries to sell you big data, then I might follow as the tech guru and tell you a little bit more about what we can actually do. But we'll see. So this represents some of the things that Ingrid was talking about, some of the motivations for why you want to do big data, and which is basically that there is a lot of data, right? And everything you do is somehow being stored somewhere, and by combining this, you can do some creepy stuff. Now, there are other motivations to do big data. One of them is this, science. This is from CERN, the Large Hadron Collider. This thing is producing tons and tons and tons of data, so much that there is no way to analyze this manually. And the only way you can do that is through some analytics. Now, people are also looking not just towards the atoms, but also to the skies. And so there you have typically other kinds of data, lots of multimedia, where you have to do some analysis on spectrum and things like this, but also represents a huge amount of data. And if you think about most of the progress being made, it actually has to do with data analysis. When they're developing, when they're discovering planets, for example, this is just based on data analysis of very small movements that you have to, or patterns that you have to find. Closer to home, we can think about biology, and I could actually advertise that there's a lecture by Nextcode, which is a subsidiary of Decode, on Monday at lunchtime in RU, where there will be discussion about the big data stuff that they are doing. So if you're interested in that, you should come and listen to this talk. So there are many motivations to do this. One more, which is typically data on maybe slightly smaller scale, is the government data that could be used to make better policies and basically make our lives a little bit better. And so that's another motivation to do this. Now, we have all these motivations, and then we can look at this. Somebody made this nice picture, very complicated, of the landscape of tools. So at the bottom you can see technologies, which I would say sort of data management systems. On top of that, there's infrastructure and applications. I think Magnus is going to come and talk a little bit more about some of the, I guess, the infrastructures maybe. Maybe going up into applications, but I want to stay on the bottom with the technologies. So when we start talking about technologies, we basically need to know what the requirements are for software. This is important to know what the things should do before we can start designing the database system. And so when we start talking about requirements for big data, basically what people throw at us is typically alphabet soup, right? So the most common thing, of course, is the 3 V's, which you've probably heard of by now if you listen to somebody that waves their hands a lot, right? So, and of course I'm doing for those of you who know Bubbi, he had once said the award is 3 million, 3 million. Now, of course the first of the 3 V's is typically volume. It's just lots and lots and lots of data, right? The second one is velocity, it's coming at you very fast, you have to be careful to store it and so on. And the third V is variety. It's complex, comes from a lot of systems, it's describing a lot of things. And then the fourth V of the 3 is veracity. There might be some doubts about whether the thing that you're getting is actually true, and what is it representing, and the complexity of that. There might be discussions about the validity. Are the data that is coming in, is it correct? Is it describing the things the way they are? There might be questions about the viability. We have a particular thing in mind that we want to do with your data, and do the data that we gather, are they viable towards answering that? And then, of course, one more V of the 3 that people tend to forget a lot is that typically we need to have some kind of value. That value could be monetary, or it could actually be better life, or depending on what we want to do with the data. So that's the 3 V's. All right. Does that help us to design a database system? Not really. All right. So then sometimes people give us the 5 W's. So the first one is why, and I think basically the three V's that we had before, they kind of answer the why. This is why we need to have big data. Okay. Who, where, when? Well, people in your company we have the analytics, we have the database professionals, we have managers, and everybody needs to chip in. Where, you could have discussions about whether you want to store the thing in-house or in the cloud or so on. When depends on your data and so on. And then what, and that's actually comes back to the requirements. What is big data, and then what do we need to do? So the 5 W's don't help us too much either. All right. So one more letter. The 4 I's. Identification, introspection, integration, immutability. And this is actually coming closer to requirements for big data. If we want to connect things together, we want to know that Yngvi is Yngvi wherever he comes up in the thing, then we need to have a good identifier for Yngvi. And so in Iceland, of course, we have the wonderful kennitala. People like attributes about identification. For example, with an identifier, you should not be able to learn anything about the person. So kennitala is not really a very good identifier, I have to say. But basically, if we don't have good identification, we cannot do analysis. This is impossible. We can do maybe mass scale things, but if we want to learn that Yngvi is pregnant, we need identification. Now, introspection, so I kind of had to think a little bit about this. So that's basically metadata, for those of you that know metadata. And for those of you that thought about using metadata that decided it wasn't worth it, well, for big data, you need it. Big data is going to come from many sources. It's going to probably last for a while. And so if you don't have the metadata, then you'll have issues with losing data because you don't know what the heck is in there. Integration, again, many sources, things coming in from lots of different places, and so you need to worry about the integration. And then the immutability, which is basically you don't delete, you add. So, even if we go to the store to return something that we bought, this is actually a new record. It's not deleting the old record, it's a new record because that's information. We returned something. So you don't ever delete, you just add. So records that, whatever you decided at some point, it stays there. So this is getting closer to requirements. And but the best sort of summary of this I actually found in a textbook by Björn, which is basically comparing sort of small data projects, which is what we've all done in the past and so on, to big data. And now small data, we kind of come up with a specific question. We, might be working on this alone. We I would say instrument some software to give us some data. We gather this in a place. We have some focused analysis. When we're done with the data, we just throw it away. So this transient, it's not there to stay forever. If we find out that we made a mistake in the data gathering, then we typically just re-instrument things and we gather it again. And so it's not too big risk. So, and at the end, we understand pretty much everything about the data. So we have kind of complete analysis. So this is what we might call small data. Now, in big data, like really, really big data, then the things are a little bit different. So the goal might not be to answer a specific question, but the goal is to learn something about the health of people, about, we want to make more money. It's a big goal. How do we do this? We don't know yet, but we're going to gather the data to make more money. So it's kind of broad concerns. It's not a very specific question, but eventually we'll have the specific questions. For now, we just want to gather data. It's coming from many locations, sometimes physically from many stores, but also just from many different parts of your company or your organization or your country, depending on how this is. It's varied and it's unstructured. So a lot of the data we have actually has some kind of structure, but if you look at Facebook, for example, I mean, there's a lot of text, there's a lot of things that have, lack structure completely. And so we need to have some ways of putting structure into this. Many providers, now one of the things that I find most interesting about this, and I find that people don't really think too much about this, is that big data should be durable. If you really want to make use of big data, it has to keep on going and growing. And you basically should think about data as being there forever, because you want to keep on learning. Now, there are arguments that you might want to forget things, because sometimes behaviors change and things become irrelevant. But then that's a decision that you make. It's not because you lost a thing or because it became unusable, but it's a decision that you made to drop things. Measurements are typically broad. We basically, well, because we haven't really decided what we want to do with this, then we need to gather a lot of information. We cannot go and reproduce. I mean, if we are not gathering data, if we're losing data, then it's lost. I mean, if we're trying to capture data about customer behavior, we can't go back to England and say, can you repost all the things you did in Facebook? No, we can't. It's gone. So we need to be very careful about this. And if we are going to base our organization and our future of our company or something on the learnings of big data, then it's kind of big risk. Introspection, again, the metadata is vital. We have to have this because we have the many locations, because we have many providers, because we have durability, then it will mean that whoever is gathering the data will be gone when you analyze it at some point in time. So if we don't have the introspection, if we don't have metadata, we will lose things. And then one of the most interesting things about this is the analysis. It's basically incremental. You learn something, and actually that something kind of has to go back into the data and become part of the data, because based on that analysis and on something else, you might learn something new. And so you get this picture of a big data resource where normally when you draw analysis, you're taking from the data away the analysis. Here, the analysis is actually going back to the resource. And so the big data should live. You are gathering data into it from the sources and also from the analysts that are putting data in there. So these are some of the requirements. So it's basically not a product or a software or something. It's basically a collection of processes. So do we have a system that can do this? Magnus might say yes. But it's hard. So it's not something, you cannot take this off the shelf and just plug it in. It has to do with the way you do things in your company. It has to do with software architecture and management and all kinds of stuff. But it's really a big process. Now, one of the things that you might have been interested in knowing is basically, so what if I am doing kind of the left-hand column? I have specific questions, I have transient data, but I just have lots and lots and lots and lots and lots of it, right? And this is what a lot of people are doing, I think, is to just gathering data to answer some questions, but not really taking the big data approach. And there's a very scientific term for what you were doing if you're doing this. It's called lots of data. So what do you want to do if you have lots of data? And you can just say it's lots of data. But again, I mean, it doesn't have the durability aspect or the big risk, or you might not be gathering metadata, but you know what to do with it and you want some specific questions, you just have huge amounts of data. And so that's going into the NoSQL thing that people have been talking about is, what you do in this case. So one thing that kind of becomes obvious is that we need some kind of heavy infrastructure if we want to deal with this amount of data. We need a cloud or a cluster or something like this, because it's just too much data to store in a single server. And then we get into what's called the CAP theorem, which basically says that if you want consistency, and sorry about the spelling error, when you're stealing images of the web, then things can happen. If we want consistency, we want to make sure that whatever we write, when we write something to the database, when we read again, we will get the same thing. If we want availability, meaning that the system is always available, we just ask and we get an answer back. And if we want partition tolerance, where if the system sort of falls into 2 or more pieces due to network failures, but we still get an answer, well, then we can't. We cannot achieve all 3 at the same time. This is called the CAP theorem. Now, the CAP theorem kind of sounds like it's completely impossible to do anywhere close to the third, but we'll find out that there's sort of you can do tunable things. Anyway, but as Meatloaf said, 2 out of 3 ain't bad. And so we can actually make some progress even with this. Now, if you look at this, I mean, it's kind of, you can take the prototypical things, for example, a relational system will typically give you very good consistency, and it will give you availability to, 0.000 something percent. But it will do this by being a single server. So therefore, you have no partition tolerance. If your node is working, then it's available. Some other systems might say, well, we're always going to answer you something as long as you can actually get to one of our nodes. We're going to tolerate partitions, but then we don't really know what you are going to read. Somebody wrote in a different partition, and you read in another partition, and you will get the old data back. So that's lacking consistency. And then, achieving consistency and availability, consistency and partition tolerance is kind of easy if you just wait. So you just guarantee that things are always correct. If you lose contact with some of the network, well, then you just wait, and they will get your message at some point, update, and then it becomes available. So it's kind of easy to see how these things can be. You can completely drop one, but you don't necessarily want to completely drop one. You would like to be available and partition tolerant, but have as good consistency as possible. That's typically actually the way that people do it. Now, somebody put up this nice picture on the web, and there's probably updates to this that are showing this in kind of more detail and showing the systems that can be that sort of are on each side of this triangle. You will observe in the top right corner that there's something called data models, and if you want to choose a system, that's actually kind of an important thing. So you have the relational data model, which we know. A lot of systems have the very simple key value model, where you just have a key, which could be your identifier. And what you can do with the key is to retrieve data related to that person or whatever. So it's a very simple model. Column-oriented, it's typically something similar to a relational model, even slightly more unstructured, but organizing things by columns. And then there are document-oriented things like, I guess CouchDB is one of them, which typically store all the information about a particular subset of your data together. And depending on what you want to do with this, then you might pick one or the other. But I want to basically talk about, what are the key components of your typical store. And I think this applies to many of the NoSQL database that you find, Cassandra, Dynamo, Hadoop distributed file systems. They seem to be mostly based on these few key things. So the first thing is that they do something called consistent hashing to do the distribution. And for those of you that don't know consistent hashing, you basically have a hash function that you consider as a ring, and you assign particular parts of this ring to different nodes. Now this is showing, the nodes being sort of linearly ordered. Many of them just assign these partitions arbitrarily to nodes. But the goal of this is to say, well, what happens if you lose one of the nodes? And if you lose one of the nodes, then basically the next node on the left in the ring will take over. And if you are distributing this randomly, then some of your data will go to one node, some of your data will go to another node, and some of your data will go to the third node, etc. And so you will distribute the load nicely when your node goes away. Another thing that the systems typically do is replication. So what they do is basically with this consistent hashing is that each part of the hash function is not just assigned to one node, but, and again, typically randomly, to n nodes. 1, 2, 3, 4, 5, depending on the level of replication you need. And it seems that 3 is typically the way that people do it. And if you do this randomly and one node fails, then different nodes will take over each of these different partitions, and so you will nicely rescale the load if one of your nodes goes down or goes out. If you have a ADA node, then you just assign that to different partitions randomly, and it will take over slowly from the previous one. If you have nodes that are different, different capabilities, then you would just assign a different number of partitions to each of them, but it scales very nicely sort of up and down if you do this thing. Then people basically have this tunable consistency, saying when you write, you will get acknowledgement that the write is done after R nodes have written it. Now, and R is typically less than n. So for example, when you write, it should be a W, of course. That's a write. So if 2 of the 3 replicas are correct, then you're happy. So, and this kind of gives you the toleration for partitions, in that you don't necessarily have to have access to all your replicas to be able to do this. Same thing with reads. If you get 2 of your nodes giving you the same information, then you're happy with this. And so you can sort of tune these numbers. If you want maximum throughput, then you just set them at 1. And then you will just write, you will get something back. It might not be the right thing, but it will be something. And actually, this is if you really need high performance, and for example, with Facebook or something like that, where you just want to show people something and you want to keep them happy, and then eventually they will get the stuff that somebody else posted, then that's fine. You can do this. Your goal is to keep them happy and at it, and because so that you can advertise to them. But this is sort of a very standard way, and then on top of this, you can do some queries. Now, queries are typically either sort of a MapReduce format or some SQL variants. MapReduce, for those of you that have used it or haven't, it's a very simple paradigm where when you have data, you put it into a system, it gets replicated according to the consistent hashing. Then you do 2 operations, which is one is called map, which basically is something that you apply to all your data. And that gives you some intermediate results. Then those get shuffled to the nodes that need to process them, and you have your reduce that takes this and aggregates it. It's a very simple programming model. For some things, it's very good. For other things, it's much, much too simple. And so there's a similar system from Berkeley called Spark, which basically has recognized this, and you can run most of your Hadoop things on it, but it gives you richer semantics in that sometimes the things you want to do are actually not that simple. You need to map, and you need to flatten, and you need to aggregate, and then you need to recalculate, and then you need to aggregate some more, and so on. And so that has a much richer semantics of things. So if you really want to do this, I would actually suggest to look into this a little bit. Now, SQL variants is another thing that people do. So basically, they will create some kind of something similar to SQL, create an interpreter on top of this, but underneath you might be running Hadoop or something with these tunable consistency and so on. Now, if you really want to look at performance, there are a number of studies, some of them kind of arbitrary, but there's, this one is actually quite decent, that basically takes the particular application of monitoring and looks at several systems and basically looks at how do they satisfy the requirements they have for performance. And their conclusion was that Cassandra, which is coming out of Facebook, was by far the best competitor for this. Had actually higher latency than some of the others, but the throughput was really good. So whether this is the right system for you, I don't know, but that's just sort of one of the studies. And so, but if you are going to do this, you should really spend some time to study your requirements and what the system can do. Don't jump on Hadoop immediately. If you decide that you want Hadoop, this is fine. I have no trouble with this. But just think about it. Don't go with the bandwagon. Do your own observations and thinking. So, but basically, because we're talking about big data management, I want at the end to leave you with this. Just remember this. We have the lots of data, which we know and like and love. But if you really want to do big data, then this is pretty much what people mean by this. And that's my story, and I'm sticking to it. Thank you.